Okay, welcome to our continuing discussion on sustainable aviation. This afternoon we're going to have a focus on major demonstrations that are going on around North America, and we've got 3 speakers to entertain us this afternoon on that subject. I'll give a brief introduction, and if the speaker would like to fill in any additional details, that'd be great. Our first speaker is Scott Savian. Scott's from JETZERO. He's the Chief Product Officer at JETZERO. Just a quick little, you're going to hear all about it, but JETZERO is a startup company. Bert Guerrero referred to them this morning as being in a partnership with the DoD, working toward a commercialization of the blended wing body for commercial and perhaps military purposes. And I think Mr. Guerrero mentioned maybe carrying fuel long distances would be his interest. But Scott's going to talk to us about what's going on at JETZERO and how that ties into a demonstrator, which Mr. Guerrero also referred to, that we're going to accomplish in 2027. So without further ado, give Scott a warm welcome, and I'll turn the mic over to Scott.
Thank you, Faye. As Faye said, my name is Scott Savian. I'm with JETZERO. We're a blended wing body aircraft company out of Long Beach, California, founded by Mark Page, who happens to be sitting right over here, and his partner, Tom O'Leary. So ever since the early days of flight, where man endeavored to take off, the first 60 years of aviation were marked by remarkable experimentation in the airframe. No holds barred, try everything and just get at it. And toward the end of those 60 years, we kind of landed on a solution. The tube and wing aircraft. And that aircraft ushered in the world as we know it today. The dawn of the jet age, the reason why most of us are here, and really transformational to the world. But we spent 60 years now perfecting that same technology. The same amount of time since the Wright Flyer to the dawn of the jet age. And in those 60 years, we've driven out most of the fuel efficiency benefits. Much of it coming from the engines, a little bit from the airframe, all aimed to drive down the biggest cost factor for commercial aviation, fuel. And even as the opportunities dwindled, we got more creative and we figured out how to get more people onto a plane. We've all felt this, right? An aircraft that was designed 2 decades ago to hold 150 people with maybe 70% load factor now holds 185 plus, and it's always full if I'm correct in my analysis. And so we feel the pressure of that every day, not just the passengers, but the crew. And the airlines aren't doing this simply to get into our pocketbook. In fact, they don't make a whole lot of money. It's not easy to be an airline today. And the run up to 2020 was a successful decade, but an entire decade of profits were wiped out by one event. And that event pales in comparison to the challenge of our 2050 objectives for zero emissions. $4.6 trillion investment, predominantly in the development and delivery of sustainable aviation fuels, which we are a big fan of, but we need more of a solution. And one of the issues with sustainable aviation fuels, SAF, is we don't know what it's going to cost, even if we can get enough. And so if we assume it's 2 to 3 times the cost into an industry that can barely make a profit today, we understand there's big financial implications and technological risk for the industry, particularly an industry that's so price sensitive, where people are buying a ticket based on a $10 or $20 fare difference. But we think there's another part of the answer, and it's developing much more efficient aircraft. A much smaller investment, a magnitudes less, into JETZERO's Z4 will deliver a step change in efficiency advantage. an aircraft that delivers up to 50% lower fuel burn and emissions than the aircraft it would replace, and does so simply through a better shape. We go back to the foundations and fundamentals of physics, lift over drag, where a blended wing body has lift throughout the entire body and matches the lift with the down forces and the inertial loads. No longer do we have a tube that's going along for the ride. And the efficiency this unleashes is remarkable and starts us on a virtuous cycle where the lifting body and reduced drag from a more elegant airframe, reduced weight from a simpler structure and the need for less fuel, and a smaller engine. And as engineers, we're in our sweet spot now. We're grinding this over and over to continue to improve each of these elements because the benefits are continued through the circle. And so, as engineers in aerospace, we hold some things to be absolutely true. If you want to be more efficient, we're probably going to be less comfortable, smaller seats. If you want to be sustainable, it's going to cost more. But one of the most fascinating things we found working on this plane is that shape is not only transforming the efficiency of the aircraft, but as we get into that space, we start to discover we can transform the experience in this aircraft. Imagine a 250-passenger aircraft that boards in 12 minutes, and you get off in 5, where every single person has a dedicated place for their bag, and nobody's more than 12 rows from the entrance. We're working on these things live every day in Long Beach, California in our cabin lab. This is a full-scale replica, a full-scale mock-up that we're working in. And we're solving all these problems and more. The ability to have a slightly larger seat because we're in a blended wing body and we don't pay the same penalties. And it goes through the entire process of what we're doing. As we get into the aircraft more, of course it has a great head-to-head comparison capability against other aircraft. We can say it burns less fuel, it has less emissions. But it does so much more on the path to zero. We'll be talking about some of this more tomorrow. We'll touch on it a bit today, though. It starts with a shape that can actually go where no plane can effectively go today. Today we think of the market as big planes that fly far, twin aisle, and small planes that fly short. And then we have the elusive mid-market where there's no supply, although the demand curve would suggest this is exactly where a plane wants to go. So if we look at that in a payload range curve, we see small wide bodies, bigger planes flying far, single aisles more efficient down in the bottom, and we see the mid-market gap. We sized our aircraft to go right in the middle of it. And because it goes there with the advantages it brings, the capacity the market's asking for, and range capability driven by its efficiency, to fly 90% of the market if we looked at it as revenue passenger miles or a kilometer. And it does so with a 40 to 50% advantage out of the gate against the wide bodies with more comfort, and 25 to 45% more efficiency advantage over the single aisles with a lot more comfort, which gets really important the further we fly. If you wonder if you ever want to stay on a single aisle for 10 hours, I can tell you, you do not. And so the shape's been in development for 30 years now. If you look real close, the gentleman right here is right there. He'll be speaking tomorrow in a couple sessions. But Mark has been at this with the persistence that you can't even imagine. And he and the team here have seen this through. These folks are all on our board as well. But the effort hasn't been alone. Led by folks like Faye at NASA, they've pushed forward in key critical areas on blended wing body like aerodynamics, flight controls, and structures to make a non-cylindrical pressure vessel. And the project itself is now garnered together for our first delivery, which will be a demonstrator for the U.S. Air Force in 2027, full-scale aircraft demonstrating the lift over drag. Some of the best in the industry have come on board to accomplish this. And we believe that's going to be a watershed moment in 2027 when the numbers prove out. We're bringing new money into the project as well. Not only our investors, but our first investor was NASA, and our biggest is the U.S. Air Force. And this is non-diluted capital. And it's a team of teams, all bent on one mission. And I can't speak for everybody, but myself, I had just started an innovation and design company working with new mobility aircraft companies. Worked in supersonic and eVTOL, some laminar flow business jets. All fascinating projects and all the right projects. But when we met JETZERO and we saw what this plane was capable of and the impact it could have at scale, it became obvious to us this is the project that needed to happen. The blended wing body at scale needed to be brought to market. Now, every person on that team has a similar story. Not the same story as mine, but everyone is there almost because they're just compelled. They're compelled to do something that's going to make a difference. And we have a plan to accelerate the future. This aircraft is going to deliver efficiency without compromise. Those trades that we've seen in the past, those hard trades of comfort over efficiency or cost, we're moving past those and we're moving all levers forward. It brings a better future for any stakeholder in the industry, whether you're a passenger who wants a place for their bag and a little bit more space for a long flight, a crew member who doesn't want to tell someone you can't bring your bag on and manage bags running up and down the plane, but would rather help and make sure everyone's safe. Whether you're an airline that wants to make a profit and provide a better product to your customers, or your community that wants less noise and greener sky, bluer skies. And so when we look at this plane, and we understand it's a mid-market size plane, nominally 250 passengers, it's kind of designed for a transcontinental mission in the US, across Europe. But the impact is so much more because it can fly short haul and long haul and have the ability to cover up to 90% of the market. And this is super critical because this is an aircraft that uses 50% less Jet A right out of the gate, will go further on SAF. It's on today's engines, so it will benefit from any new engine technology to further drive those numbers down. And because it uses less energy, it makes things like hydrogen and electric propulsion more viable at scale. It's also a plane that's coming to market in 2030. And we all know on sustainability, the longer you wait, the harder it gets. So to bring an aircraft of this size and scale into the market early becomes a key potential for meeting the 2050 objectives. So that's what we mean by the future takes shape. Thank you.
Okay, we're going to stick to the schedule, so we're going to give Scott a few minutes to field a few questions before we bring up the next speaker. Next speaker will come up at 2:55, and that's Fassi, you're number 3. So where's our Brent? Right here? Okay, great. So everybody's here, but let's give a couple questions to Scott. And I think Mark is here as well, right? If Mark wants to join in as well. So questions for Scott. Anything from the audience so far? And while Ron's getting tuned up here, we will have a general Q&A at the end of all 3. This is just a bonus session here.
Super. Thank you, Faye. Ron van Manen, the Dutch National Innovation Program. Intrigued by this wonderful design. But with that market, how are you going to get to a rate 100, rate 150 per month? It looks exciting, but it also looks a little bit more complicated than that classic tube and wing.
What, 150 per month?
Something like that.
No, we're,
100 seems to be what the brand A and brand B think will be needed for the next single aisle.
yeah, I mean, right now, our rollout plan, and there'll be others at our company with more details on this, get our first facility up and running, delivering in 2030, ramping that facility to 20 a month, and then as demand requires, to copy that facility into multiple, potentially in different places. Yeah, we'll be we believe the market will follow because the aircraft will have such advantages. But could JETZERO build every single plane out there? Of course not. But if we can help compel and propel the rest of the industry forward to follow suit, mission accomplished.
Hello, sorry, I've got a mic, so whilst we're waiting for him to get a mic, Alex Dixon over here on the other side of the auditorium, here from the ATI. Your time frame from demonstration in 2027 to going in production 3 years later seems quite racy for aerospace. Can you talk us through how you're going to achieve that and maybe break barriers that we're not seeing currently?
Yeah, I mean, we'll go a little bit more into that in a session tomorrow. Thank you for the question and getting the hard one right up front. The demonstrator in 2027 will be a full-scale aircraft. At the same time, we're embarking on the production plane in parallel as we start to ramp down those engineering forces, ramp up the rest of the team. Yeah, I think in general terms, it would be considered ambitious, but we are a company with a single purpose, with a bunch of world-renowned experts working on it with, I would say, no distractions. And all that comes to our advantage for sure.
Yeah, Roland Gerhardt from Germany. Are you planning on building a family out of that aircraft design? Because you have the complete families of the A320, 737 with the different models. How do you scale that design up and down for different market demands?
I think my colleague Mark will be addressing that exactly tomorrow. If the question is, can you plug a tube and wing? The answer is yes. And Mark, I think we'll show some technical stuff on that tomorrow.
Hi, Lorenzo Mazzei, Ergon Research. You are talking about entering into service in 2030. Have you already selected an engine supplier for your aircraft?
I am, well, I'm not at liberty to say that. We're not looking for a new engine, I can say that. All the efficiency numbers we're quoting are an out-of-the-box engine as of today.
Axel Klein, Clean Aviation. A question related to the Delta technology you still require to develop in the context of the next 4 or 5 years. You said engine technology, no need to develop new technology, it's there already. What is with structural aerodynamic benefits or so? Is the technology there already and now you're maturing, or what is the technology bricks you're still requiring to develop over the coming 3, 4, 5, 6 years?
Yeah, I think on the slide, and again, Mark will be showing a bit more on the actual development program tomorrow. But there was a slide in there that said the shape is the new technology. It literally is the shape. We're off-the-shelf systems on everything we can possibly do, and that's being proven out in our demonstrator program with some of the partners we showed up there. and then we're driving forward with how to deliver the shape, not only the aerodynamics, but the manufacturing. Right, we're in a world now with advanced composites and manufacturing that we didn't have, years and not even decades ago, but just years ago. And so we're leveraging all that, including a lot of work from NASA in that exact category.
Thank you. Moreira from Technical University of Munich. I was wondering regarding infrastructure, if you're designing for 100% compatibility with existing infrastructure, if there are any changes from that perspective that would be required to operate your aircraft?
Great question. This is actually one of our most interesting things. We have a very wide wingspan to length ratio, and today we fit inside of a Type 5 gate, no problem. It's an aircraft that would turn in a Type 5 gate in a fraction of the time of that type aircraft, but we're also getting creative on how to use airports as they exist today. Beyond that, we do have potential for future wingfold to get into smaller gates as well.
Question, and you answered it pretty
Thank you.
Okay, let's see. Our next talk, got a little model to set up. We'll get into some work that that NASA is sponsoring, and along with Boeing. So it's another public-private partnership. NASA has a few people at the conference this week. We're very lucky to have Brent Cobleigh here, the project manager for the X66 project, to get us started. And Brent will have a speaker that he'll introduce as he gets into his speech, which will start right now. Okay. Over to Brent. Thank you very much. Can you use these guys? Or I think I'll walk around. Okay.
Thank you very much. It's good to be here. I'm going to kick this off and then turn it over to my counterpart at Boeing to tell you a little bit more about the X66 aircraft. So this, we had to shorten the title a little bit, but it's really the X66 Sustainable Flight Demonstrator Project. And so you see an artist rendition of what this airplane is going to look like when we get through. But we really want to talk today about how we're developing and going to build a full-scale demonstrator to really target certain technologies. What are those impediments to trying to get an airplane like this to market? So let's kick that off. I'm just going to tell you a little bit about, start off with the why we are pursuing this aircraft and this project. So NASA has been looking at the field of configurations. We've been working on advanced airplane concepts for decades. Faye actually ran a project about a decade ago that really dove into many different configurations and built some of the models you saw earlier that have been flying subscale models. And so we're very familiar with blended wing bodies and transonic truss brace wing. We've been working with industry for about 15 years now. And there's been a lot of other configurations come along the way, both from industry and government and universities. So the problem is, I don't know if any of you saw one. I didn't see any of these aircraft out on the airports this week while I was flying here. And so what is that? What's causing industry to hold back and not pursue one of these advanced configurations? So a lot of the reasons for that are pretty obvious. There's a lot of competitive factors. There's the enormous cost. We're talking about tens of billions of dollars to launch a new aircraft and get it from design all the way through certification. There's lots of technical risks and manufacturing challenges, so it's not just about the outer mold line of the airplane or the efficiency. Like I said, we've been doing wind tunnel testing and subscale testing, so we know what the efficiencies are, or at least close to that. What we don't know is, how do you build one of these different structures? How do you certify them? What are the challenges of making thin wings, for example, and getting them integrated? So it's all of these questions. We set up this project around how we want to have a competition with industry, and the goal is industry tell us what is holding you back. What are those questions you need to answer in order to make the decision to, hey, we're going to go pursue this airplane and turn it into a production, a production vehicle? And so we did a competition around that. And the goals for this project really to partner with industry, and this is a significant partnership both in support and labor and money, to retire as many of those technical and manufacturing risks as possible, to inform your decisions for the next vehicle. So we did have a target time frame. It was not, what can you do in 2050? It was what can you do in the 2030s? We really need to do something aggressive against these climate goals we have, and that's not going to happen if we're just pursuing something that's going to take several decades to get to market. And then, of course, you heard earlier about the U.S. Climate Action Plan, and so our project's in alignment with that. So how did we do that? So we actually picked a different model than what we're used to using. We usually use some kind of a government contract to pursue an activity like this. And what that requires is the government goes out there and writes all these requirements and tells industry what we want them to do. And we have all these deliverables, and it's very constraining. It really aligns the whole project around what the government wants. We didn't want what the government wants. We want to know what industry needs in order to pursue this technology. So that's really how the proposal process went. We had multiple bidders. We went through a proposal process, and we ended up awarding a Funded Space Act agreement. So what's unique about a Funded Space Act agreement is it's really not government-led. It's industry-led and government-supported. And so they write the requirements, they lead the project, and NASA supports that project. So NASA, in this case, is providing $425 million over 7 years of direct payments. When certain milestones are met, the partner gets a payment. And then we're also supporting, in addition to that, with some labor support and some facility testing support, which I'll mention a little bit on my next slide. Boeing is going to be providing a significant amount of resources too, and in fact, more than the government. They're estimated at about $700 million. So it's really, we wanted to have skin in the game, and that's what industry came forward with. We got to put your money where your mouth is and show us that you really want to pursue this and have a plan to move forward. So the other unique things about a Funded Space Act, they're going to own the airplane at the end of this, and that was fine with us. If they really are going to pursue this kind of configuration to a commercial market, they may need the airplane to test other technologies that would go along with that later. And the other big thing is, these projects are very expensive for NASA, for anybody to do. This project alone is probably 10% of the aeronautics budget. And so we couldn't really carry the risk of this thing overrunning and cost a lot more. So industry knows ahead of time they're carrying the risk. Our contribution is limited to the $425 million plus the NASA support that we committed to. So they're carrying the risk. Follow on. So I'm just going to say real quick what NASA's role in. I'm going to turn it over, and you're going to hear a lot more about the airplane and what they're going to do to manufacture and build it. We have kind of two major roles NASA does. We support the Boeing technical teams with some of our subject matter experts at NASA. So we assign people to the propulsion team and the computational fluid dynamics team and ops teams and so forth. So we have kind of people sprinkled around to the different integrated product teams that Boeing has in place. So they're just supporting, bringing in NASA expertise in different areas. They can reach back to other NASA experts to help solve problems. But really the most visible support is in the area of the capabilities and testing and ground operations that we're going to support along the way. We've got wind tunnel testing that's actually in progress as we speak. The one that says the low-speed test up there, we just completed some testing in the Langley 12-foot tunnel. We're actually going back in, I think, this week or next week to do some more testing. That's just a 3D printed model, printed really quickly, and we learned a lot more from that than I expected. And then the upper left picture is a half semi-span model that's currently being tested at NASA Ames in the 11-foot tunnel. This one goes up to high-speed transonic conditions, and that's a very important model to get loads on the wings to verify your predictions. NASA and Boeing together are both doing computational studies. We have different techniques, we have different codes. It really helps to have multiple codes to do that kind of work. Down in the lower left, you see we're developing a piloted simulation at NASA. Boeing also has some simulations to do avionics and integration testing. And then we'll be doing some structural testing of the truss that you see on the truss brace wing eventually, at least one of them. And then when we get to the flight test part, we'll be flying at the NASA facility there with our chase aircraft, mission control rooms, and we'll be doing that work jointly with the Boeing team. So it's a really, really good collaboration. And so I'm going to stop here and let Eric take over. Eric Caduce from Boeing, he's the program manager for Boeing. And like me, he's hitting close to 30 years with Boeing, and I'm about 30 years with NASA, so we got a lot of experience to bring in and hopefully guide this program in the right direction. Thanks.
All right, thanks, Brent. All right, hey, thanks everyone. I'm glad we got through the system of systems talk earlier, right, Jim, because I get to talk about the airplane. And I set a timer here because those of you who know me know when I start talking about the airplane, I tend to go over my time a little bit. So as Brent said, this is a joint NASA-Boeing project. It's been a great relationship so far. It's one of the best parts about this is being able to integrate our teams. We actually have NASA engineers embedded with the Boeing teams working on through some of these really difficult problems. It is an MD-90. For those of you who aren't familiar with the general concept, we took an airplane from Delta Airlines that got retired during COVID, and they gave us 2 of those airplanes actually, and we flew those, brought them out of storage about a year ago, flew them to Palmdale, California, where the final modifications will be done. And then from that, we will do a minor modification. We'll take off the engines, we'll take off the wings, we'll take 19 frames out of the front of the airplane to rebalance it, and then we will install an all-new composite wing, fly-by-wire lateral controls, a new geared turbofan from Pratt & Whitney, and then update the rest of the systems through the mid-body to reintegrate the original landing gear from the MD-90. So that's in a nutshell the program. Now the details are all, of course, much more challenging and much more specific, which is why we build the airplane in the first place. And I'd actually like to applaud my friends over here at JETZERO. There's nothing like building an airplane to drive home the realities of aerospace design. Right, there's philosophical conversations around aerospace, there's academic conversations around aerospace science, but when you're gonna go put 8 of your friends on the airplane and carry with it the reputation of your company, things get extremely real really quickly, right? And there's no such thing as a small problem anymore. And those are the kind of things that you have to do to drive forward the science of aerospace. This airplane is not configured to be a product, and I have to mention this all the time because I've actually had people come up to me and say, well, how many seats are on that? And I answer 8, right? And then they look at me funny like, well, what are you doing? It's like, well, it's 2 pilots and 6 flight test engineers. It's not configured to be a product. It's configured to be a laboratory that flies, and it's going to teach us everything that we need to know to take the next step or to make the decision if we're going to take the next step for an airplane that looks like this. And those questions are actually fairly significant. Now, things like aerodynamic performance, we kind of know that. Like CFD is actually pretty good here, right? Being able to predict the high-speed cruise characteristics of an airplane that looks like this. What's a little harder is like, how does this feel to a pilot? If you're gonna go replace 20,000 airplanes someday and grow the market to 40,000 airplanes, how is that going to feel to the pilots that are going to be flying the airplane for the next 60 years? Thin wing integration. That wing has all the systems of a 737 with 1/3 the internal volume. That's one reason we're building a full-scale flying demonstrator, because systems don't scale very well. And so if you try to do this on a subscale airplane, you're not necessarily going to learn everything you need to learn to convince yourself and de-risk the technical development so that someday you can go, you know what? This is actually a pretty good idea, and we're pretty sure that if we make a commitment to this architecture, we're not going to find something 3, 4, 5 years down the road that is going to make us regret that choice, right? And then, of course, the loads and dynamics are very different on this. This is a statically indeterminate wing. It's not something we're used to dealing with in commercial aerospace. So all the tools, methods, processes, correlation of all that data needs to be done to not only evaluate the program and the technical development of the airplane, but shrink the uncertainty window. Uncertainty is not your friend when you're trying to go make a $10 billion commitment to the next new airplane, right? So one of the things the X66 is going to allow us to do is shrink that uncertainty, correlate tools, be able to take that data, configure a commercial variant of this type of architecture, and then with some definitiveness, make a commitment to this architecture as the thing that's going to replace the 737 or not. And even if not, by the way, there's a lot of technology that's going into this thin wing and this architecture and the materials and the fly-by-wire systems and a vehicle management system computer that would have direct and real applications to anything that we would do next. All right, I just couldn't resist putting the picture of our esteemed chairperson here. This is the model that is currently in the NASA Ames 11-foot transonic tunnel, semi-span model, 700 pressure ports. It is the vehicle that will generate most of our external loads, which will of course get turned into internal loads and structural sizing. That will take us through preliminary design review of the vehicle. So that's a super important piece of hardware for us. I believe that test wraps up on Friday, so it's been a really successful test so far. The technical maturity of the airplane is advancing rapidly. We are learning a lot. We talk about the airplane talks to us. The airplane talks to us every day. Sometimes not always nicely, right? But it's always giving us feedback on the things we try to do, primarily around structural load paths, the close coupled nature of the aerodynamics, the structural design, the systems integration. These things, of course, are all very important on a commercial airplane. It's really important on this. Right? The things that have some sort of dependency on a typical commercial airplane have a high degree of dependency on this airplane. So structural sizing, joint architecture, the wing-to-body fairings, the fairings that go around the flap tracks, the airflow through some of the channels on the wing and the strut and the jury strut and the engines. These things are all very tightly coupled, and when you modify one, it has ripple effects on everything. So we're learning a lot about all those interactions, which will ultimately allow us to optimize all of this geometry someday, should we choose to pursue this on our commercial platform. We've selected our major suppliers. They are under contract, they're working with us, they're embedded with the team, so we've been able to actually exercise some of those relationships as well and something outside of a traditional commercial certification realm. So it's been really interesting to start with like a co-development of requirements as an example on an airplane that looks like this, rather than just like Brent talked about with the Fund to Space Act agreement, just providing a set of requirements and seeing what we get back. So that's been an interesting side benefit of this program as well. As you can see here, the wind tunnel testing is underway. We'll be out of that tunnel this week. We'll be entering back with our full span tunnel test later this year in that same facility. And then early in 2026, we'll be at the Kinetic facility in England doing a pretty extensive low-speed wind tunnel test of this configuration. We have our airworthiness and product safety and integrity requirements complete. This is actually a fairly interesting deal. Because we haven't done anything like this, and I neglected to mention here, since the 707 prototype. The last time the commercial aerospace industry built a full-scale flying demonstrator, and now we're going to have two, was in 1955. And that revolutionized, the way we look at air transport. So we're doing it again now. But because we haven't done it so long, our own command media didn't tell us how to proceed, right? We either do things like a one-off flying demonstrators of a 10-pound drone with scientific equipment, or the 777-9. This kind of thing in the middle doesn't have a lot of guidance, either from the regulatory agencies, from the Boeing internal processes, from our suppliers. So we had to create this infrastructure around, well, how do we do this? Right? And there's peril in both directions from a program management perspective. Too much infrastructure, and it's a commercial airplane program, right? And it's not something that takes $425 million from NASA and $725 million from Boeing. It's something that takes $6 billion, right? And no one can afford that, and it would take too long. Too little infrastructure, and now you're skating that edge of, well, how much like product integrity and safety and airworthiness requirements do I need to bring along from my heritage from commercial aerospace to make sure the vehicle is first 100% safe to fly, but two, and maybe just as importantly, representative from an architecture perspective of what we would eventually build, right? If it's not representative, if it doesn't mimic in every way possible a future commercial product, then the learning gets eroded. And that learning and reducing that uncertainty is still the most important part of this program. And finally, I'd be remiss if I didn't mention that we've actually been able to pull together an incredible talent pool to go do this. It's probably not a surprise that when I go out to my Rolodex within Boeing or to industry and I say, hey, who wants to work on an X-plane that has the future of revolutionizing commercial transportation? I get no shortage of like some of the really smart people in industry going, oh, ooh, pick me, right? And so we've been able to do that and put together a really high caliber team on the NASA side, the Boeing side, and from our suppliers. So that's been a joy, part of this program. I can surround myself and the team with people who are really passionate about pursuing this, and it makes coming to work really, really fun. And from a program management perspective, kind of easy, because the team's motivated. Really, my job just is like now get things out of their way and let them do their magic. All right, based on an MD-90, like I said, we're taking 19 frames out of the front. This just worked out. Sometimes you get lucky. The production splice between an MD-80 and an MD-90, anybody want to guess? It's 19 frames, right? It just worked out. That's exactly what we needed to take out of the airplane to balance it when we took the engines off of the tail and put them on the wing. So, and it's a constant section splice. Thank you very much, McDonnell Douglas. So that's unbutton a couple circumferential splices, move the nose section forward and rebutton it back up. So we couldn't have gotten much luckier on that one. All new fly-by-wire composite wing, leveraging the technology, of course, that we developed in the 787 and the 777-9. It is a multi-spar, which is a little bit of a different arrangement for us. That is purely geometry-based. When you have a thin wing, if you have stringers, the stringers kind of want to touch. And once they touch, they become spars, right? So that's just a fact of the geometry. But that's an interesting learning for us to figure out how we would go produce a wing that looks like that, and then probably more important, how you would service it and maintain it, because the access to this wing is certainly more challenging than it would be on something like a 737 or a 777. Hybrid metallic composite truss. So there's a lot of titanium and steel in that truss that actually carries quite a bit of load, which you want. The truss is working, right? We see that through our loads analysis. And interestingly, it's both a tension and a compression member, so it's sized accordingly. This is the first time we've evaluated something like a triplex vehicle management system computer, typically used on more of a military application. So it's a good opportunity for us to try out a vehicle management system driven by redundant computers on an airplane like this. It actually gives us quite a bit of advantage in terms of eventually putting on some fairly sophisticated flight control software and algorithms on them. The original X66 will be relatively simple in terms of its flight control architecture, but as Brent said, it's Boeing's airplane afterwards. And so it'll continue to be a test bed to evaluate that architecture and the benefits that we can get from it. We're going to keep as much as the MD-90 flight deck as we can with minor modifications, mostly for engine controls. And then we're going to keep the MD-90 landing gear, wheels, tires, and brakes and retained. It's actually the pivot point is in the same spot, like to the inch, as it is on the MD-90. Just worked out that way with the geometry. And of course, we're using a derivative Pratt & Whitney PW1900G engine, which is the first time that Boeing's put a geared turbofan on any of our products. So it's also a good opportunity to get to know that engine. And really understand how it works on a large-scale commercial platform. All right, technical maturity is advancing as well. I had this really beautiful picture that I wanted to show you, but the lawyer said no. But it shows you how much integration work we've done to really pull the airplane together and get everything to fit in that wing. That was a task, and it continues to be a task. And like I said, it's very closely coupled. You change one thing anywhere in that wing, and the ripple effects go all the way across it, right? And then you have to chase those down and put the airplane back together effectively. External and internal loads being generated from the wind tunnel, so that's a very important learning, of course, and we'll get into more detailed structural sizing, which again really comes into play in terms of the spatial integration of this wing. The systems architecture is coming together, suppliers are on board, we've got everything integrated, all the systems are sized, primarily using off-the-shelf or modified off-the-shelf systems, which expedites the process, and it kind of isolates the variables, if you will, because I don't have to then figure out how much of any system performance is from a new systems architecture or a new systems component. Those are well known. The production system, the logistics, and the build sequence is actually way ahead of plan for an airplane of this phase. We know where we're building it. We know the transportation plans. We know the sequence of of the build. We know the condition of assembly for everything coming in and how it's going to go together, so that's going really well. And then we're just getting into our laboratory test requirements and the facilities built. So these are things like a flight controls test rig and an electronic power lab and avionics systems benches, which eventually will turn into the full-scale piloted simulator that Brent mentioned. All right, and just a reminder, these are the kind of things we're trying to learn on the program, right? These are the big learning objectives. So I talked about thin wing integration already and the relevant high lift systems architecture. Very thin, it's hard to get a high Fowler flap system integrated into this wing. Static loads and methods validation, including and additional CFD validation, these are all really important. A lot of our tools and methods and processes have been organically derived and built up over the decades to do tube and wing verification and validation. This is different. So once we fly the airplane, we can go back and do close correlation with that data, and then to make sure that what we think our tools are telling us is how the airplane is actually responding. I already talked about the flight handling characteristics a little bit, and the structures, internal loads as well. Those joints are quite sensitive, especially in the critical areas of the wing, so we've done a lot of work at what that joint architecture looks like on the X66. I love and hate this chart. This is the how do you build the airplane in 23 easy steps. It looks like we should be done like Tuesday, but there's some real big ones in here. But I mentioned that we've got a pretty good understanding of what the build sequence looks like on this airplane. So we are on step 2 right now. The engines are off. We're about to, sometime in 2020, late 2025, we'll start the heavy modification, take the wings off, and take that fuselage section out, and then we will begin fabrication of the wing sometime late 25, early 26, before bringing it to Palmdale in the 2027 timeframe to begin ground and taxi testing before we fly in fourth quarter 2028. And I think just a little bit more on the schedule before I open it up to questions here. So right now we're definitely in the design phase, learning a lot about the airplane on the daily. We're about ready to get into some of the testing that will take us beyond just the usual wind tunnel testing and start getting us into a digital simulation of the airplane, getting our power lab set up, our flight controls test rig set up, avionics systems bench in operation. We have a functioning piloted simulator right now in Long Beach, California, so we're starting to run stability and control, handling characteristics and piloted simulation there, and getting direct feedback to our engineering teams so that we can make modifications as required to the airplane and the flight control system to get the handling characteristics we want. We will get into fabrication, like I said, toward the middle of 2025. Heavy structural mods will begin about that time as well, and once that starts, we'll have a full shift in Palmdale, working pretty much for the next 2.5 years, getting the airplane stripped down, taken apart, the new wing and strut coming into the facility, installing all the systems, and then getting the functional test, final assembly, functional checkout, ground test, and taxi test, and then flight. So it's an exciting time for X66. We've already learned a lot about the airplane, the integration, what it's going to take to commercialize this someday. So the whole purpose of the program so far has been extremely successful. We're looking forward to what comes next. We're in the hard part of getting through PDR and into drawing release. On the daily, we're discovering new things that need engineering focus, but that's the point of the program. And so far, we've been able to deal with everything that's come our way, all the lessons learned, integrate those into the vehicle design, and moving forward towards a successful test and flight coming up in the next few years. All right, thank you.
Nice job, thanks. We're going to hold questions for Eric and Brent to the end because we need to move on to the next speaker now. Be sure to hang around for the Q&A period, which begins at 3:45 after Fassi is complete. We're going to do a quick laptop change here. Okay. While we're doing that, I'll just do a brief introduction for Fassi Kafyeke of Bombardier. I've worked with him for quite a long time. We've actually compared notes on some of these things, and I think you're going to hear a pretty exciting story from the work that Fassi and his team is leading from Bombardier perspective. So I'm going to turn it over. Fassi, if you want to add any additional details to your background, please feel free to do that. Also, we're not recording this session, as I understand it. This speech will not be recorded.
TTWB. The first is, or maybe it's a question to NASA as well, who owns the IP? If this is a shared funded project, 1/3 coming from NASA, 2/3 coming from Boeing. Boeing owns the aircraft later on, what we've learned, but who owns the IP? That is the first question.
Yeah, so I mentioned earlier talking about this unique procurement instrument, the Funded Space Act Agreement. So one of the unique things about a Funded Space Act Agreement is since industry is putting in a huge amount of money, we can't ask them to, we can't go out and publish all of their IP. So it gives them the most protection for IP. They can basically mark things as proprietary as they go. Now they recognize we're working together on things. We're gonna publish some things, but it'll always go through sort of a review on their end before. So it is, Funded Space Act is not something we're gonna use in every case because we're a research organization. But in this case, the goal was not necessarily developing the research because we had done that over the last 15 years. It was about what can we do to actually take this research and get it out there so it's actually improving the environment.
Okay, thank you. The second question then really goes to Boeing. What is your certification baseline for this X-plane? So you said 100% safe, but we know that's not existing. So what is your baseline for that to certify that? Is it with respect to bird strike and everything? How much effort will you put in? It's not a CS-25 aircraft, I guess. So you have to be somewhere in between with respect to safety requirements. What is your baseline on that?
It's a great question. So we start off with, first of all, NASA is the Airworthiness Authority. So there's a joint NASA and Boeing Airworthiness Board. Each one has an independent vote. The airplane doesn't fly unless both of those boards give it the thumbs up to fly. It's based off of a MIL Handbook 516C set of safety criteria that we are using applied FAR Part 25 criteria to satisfy. So if there's a MIL Handbook 516 requirement, largely we will go look at how we would satisfy that requirement to the FAA or EASA as a Part 25. We're certifying the airplane to attend to the, not certifying, we're qualifying the airplane to attend to the -7th from critical failure cases, but at a exposure level, since this airplane will likely have fewer than 1,000 cycles or 3,000 hours on it, it actually has a higher degree of event probability over its life than a commercial airplane.
Roland has one last question.
I have one last question, yeah. So a couple of years ago, we've seen a Boeing presentation where they had two projects. One was a truss-based wing, and the other one was a blended wing body. So in the end, you went with that solution to proceed only with that solution. The other two presentations were a blended wing body. So why did Boeing decide on the truss-based wing and compare to the other solution with a blended wing body?
It's a fascinating question, and I think the aerospace industry is replete with these kind of interesting competitive competitions. Boeing certainly has participated in other blended wing body type activities in the past. Including X-48. Just the transonic truss-braced wing to us means it's easier to fit into existing infrastructure. It works largely well with the airport compatibility, the ground service equipment, the airline reservation systems, existing maintenance training. So it fits into the airport infrastructure pretty seamlessly from that perspective. Obviously, the wingspan is something that we would have to deal with, but frankly, anything that's trying to reduce fuel burn and emissions over the next 50 years is going to have to deal with a fuel or a wingspan limitation anyway. But on top of that, there is the element of we think it's easier to satisfy a larger portion of the market with a non-recurring cost that the industry could bear. To be able to satisfy somewhere between, 130 and 210 seats or maybe even larger without radical changes to the airplane architecture.
Thank you.
Fred Abbing from the Netherlands. Thank you very much for very interesting presentations, 3 presentations. But my question is with respect to the X-66. I've been reading the sugar reports and all the studies that have been done by NASA and Boeing, and I remember that they started at a cruise Mach number of 0.7. They said this is the best, the optimum solution. Also, if you look at the FAA Ascent studies, Project 10 and Project 64, they said Mach 0.7, that's the optimal. Can you explain why gradually you moved to Mach 0.8, if I'm correct?
Yeah, no, great question. It really comes down to the learnings that came out of the sugar studies and a better understanding of the aerodynamic phenomena, especially in the channel flows with respect to the wing, that we're pretty confident we can engineer out the drag penalties associated with that configuration that had the earlier studies suggested a lower cruise Mach. So, sure, but a 737 will burn more fuel at 0.75 than it would at 0.7 as well, and then you have being able to fit in with the scheduling infrastructure throughout the rest of the industry as well. So it's a choice. Right now, the X66, keeping in mind that the X66 isn't the commercial variant, right? It's a research opportunity. So we will be flying the airplane as a design cruise Mach at 0.79. Well, again, for the X66 perspective, we'll validate the models, right? We'll transmit that data to Boeing Commercial, and with that information, they can make a strategic decision about how fast a transonic truss brace wing 737 replacement would want to fly in the light of the sustainability goals.
Oh, I'm next? Okay. Yeah. Hello. All right, thank you. Sorry, another X66 question. I know there's a lot of aerodynamicists around here, but I'd like to talk structures a little bit. I think just very interested, I'd love to see some of the load cases and you know, the FE models on the configuration to just understand how it's actually working. But just in particular, you know, thin, tapered, and some other interesting effects for the composites just makes me think about special aeroelastic problems and perhaps weight penalty associated with that. Could you just talk a little bit about that?
Yeah, I can talk a little bit about that. First of all, the truss is extremely effective, right? We see that in...
I'm sorry, I'm thinking about outboard of the truss was in particular.
Yeah, but because the truss is extremely effective, it effectively treats that outboard wing as if it was outside a body. Right? So yeah, it's thin, it's swept, but the presence of the truss changes the dynamic loading conditions pretty significantly, right? So we're seeing the benefit like we would have expected. We will be conducting some additional flutter tests in wind tunnels coming up to validate those models. But everything that we've seen so far would indicate that that truss is working exactly like we would have expected. It's restraining the modes outboard of that structural integration, and the outboard wing is pretty well behaved right now.
By yourself?
Hi, thank you very much for your presentations. I really enjoyed them. I'm Javid Bayendor from the State University of New York. I have lots of questions, but I try to just cut it down to two. The first one is that it is perhaps for Brent and Eric. I noticed that your exhaust starts exactly at the leading edge of the wing. That causes enormous amount of negative pressure under your wing, and it would reduce your drag significantly. So your only outer board sort of wings are creating lift, whereas the middle wing will lose lift. So have you looked into that? It would create a negative load for the root as well.
Yeah, without getting into too much of the details there, that engine's pretty strategically placed so that the thrust effects of that engine flow through that triangle between the wing, the strut, and the fuselage in the way that creates the least possible amount of interference.
So when you did the wind tunnel test at Ames, was the engine fake engine, or you actually had the engine working?
They weren't powered at Ames, yeah.
They weren't, so you wouldn't be able to, you wouldn't have been able to see the effect of the...
Not from that test. We have other methods of, we have other methods of validating the flow fields through there.
Well, thank you. The other one is for X66, if you don't mind. I, many years ago, had the privilege to meet with Dr. Richard Seabass. He's the sort of modern era father of the blended wing body. He passed away since, of course, but we had long discussions about this system. I was wondering, you didn't show exactly the inside of it, but have you been able to move away from double bubble or multi-bubble to be able to cancel the loads from the wings, or how have you sorted that that problem? Because it's going to create a shear that would rip the fuselage to half.
So that's a question for the BWB teams, if I understand that right. Is that right?
Yes, I'm sorry, yes, for JETZERO.
JETZERO, got it.
So we are a non-cylindrical pressure vessel, and this comes with, when we were talking about the challenges of shape. Exactly how we're solving it, I don't think I'm privileged to talk about today. If we are, Mark may get into it on tomorrow's session a little bit, but it's integral to our design how we solve that problem.
Could I invite you to look at the paper that was published in 2006 ICAS or 2008? It talks about the internal bracing of the blended wing body from RMIT at Melbourne, Royal Melbourne Institute of Technology. It addresses that problem about 18 years ago.
Yeah, thank you. I think Mark may be familiar with this one, and this is actually one of the things we work every day with our structures team. So it's an integral part of our development here. But I don't think I can share more at that point. Apologies.
Thank you.
More questions? We still have a few more minutes. Yes, question here. Yeah, that much I can see, I think.
Thank you for your presentations earlier. John Couldrick from Australia. With respect to Jim Holman's presentation earlier about we need to think about the ecosystem, the aeronautical ecosystem, how much interaction or engagement have you had with infrastructure owners like airports? Because I see all the designs having massive impacts to the airports themselves. Have you had any engagement, or have they reached out? Have you reached out?
Yeah, I think this is probably a bit of a future problem as we get longer and longer wings, as we've seen. It's a key part of our efforts today. We happen to be on the airport at Long Beach and interact with those folks, and it's a significant effort on our side with the airlines as well, and our airline working groups, to literally drive down through those solutions.
Yeah, similarly, we have an airline sustainability coalition that advises an X66 that comprises of the 5 large domestic airlines from the United States, so Alaska, Southwest, Delta, American, and United. So we have those conversations with them on a regular basis. Boeing also, of course, has an airport compatibility group. Is their day-to-day charter is working with the airport infrastructure around the world on not only wingspan, but fuel storage, jet bridge capability, airport throughput, takeoff and landing times, runway approach separations, all those kind of things. So this is something, wingfold, yeah. I mean, of course, the 777-9 has a wingfold capability on it, which will be in service here shortly, and then we'll start getting that in-service experience of operation with wingfold technology in the airplane as well.
Fassi, you want to take a crack at that?
I think for a business aircraft, a small aircraft, that is not a big problem. We fly to the same airports that our current business jets fly. I think the more problem we have is operational. How do we do the maintenance? How do we do the luggage? So we have teams that are looking at that. Other than that, we work with the certification authorities, Transport Canada, just to brief them regularly and make sure that whatever aeroplane we come up with is some aeroplane that will be able to certify.
I think the good news is, well, one, we're not something as disruptive as like an A380, but I think the best news we typically get from the airlines is if you deliver those efficiency numbers, we will figure out how to get it into operation, which is encouraging.
Guys, fascinating session. I'm Chris Atkin. I am the program chair for this Congress. Want to pick up on the last question, also Fred's question about cruise speed and something that Axel said this morning about getting the regulators involved. So we're seeing a number of different solutions here. And what if, you know, you really push towards an optimum, which is going to change approach angles, descent angles, cruise speeds, ground infrastructure. If there was a single solution, yes, you could take the community along with you. If the community is faced with three different solutions that have three different impactors on certification and operational infrastructure, what's going to happen then?
Yeah, I think what you're saying is if we have, you know, three competitors come into the market and we each have a unique geometric solution that has different airport compatibility considerations, like how do we decide, right? Because there's only so much money and energy within the system to update the infrastructure. I mean, I think that's a fantastic question. It's one of the reasons that Boeing has gravitated toward the TTBW configuration, because we assess the requisite changes to the airport to be smaller than maybe some other configurations, and we can focus on those things like wingspan and gate-to-gate compatibility and runway to taxiway compatibility that would be sort of universal, right? Regardless of whether it's a blended wing body, a transonic truss brace wing. I think some of the other things that would come around with let's just call it a novel architecture, be it BWB or anything else, right, are on, I don't know, fuel trucks or water tankage or like those things, like, you know, typically the industry has worked. You know, like you were saying, if there's benefit, the airports have found a way. But I think span being the universal challenge, and then things below that were, you know, might be more configuration specific.
Want to add anything to that? Brent? Roland has another question.
Yeah, sorry, I have another question for JETZERO. You said that you got some funding from the Air Force. Are you working on a different model for military operations, or will it be some cross-financing for civil operations or something?
The Air Force demonstrator in 27 is, I couldn't put a number to it, highly similar to the production plan. But we're learning as we go, right? So we have a little bit of time to continue to evolve as we work forward toward 2030.
5 more minutes for questions.
Hi, thank you very much for the presentations. Matt Ersendanen from Sistea. I really enjoyed the mention of Heathrow this morning. For an airport operator, climate risk is often thought about in terms of the physical risks of climate change, but actually what's more of a risk is how on earth do you bring in all these new technologies, particularly SAF. So we're heading to a situation where we have 4 different fuel types, potentially 2 or 3 different airplane types. I just wonder at some point, do airports have to specialize and limit themselves to what type of aircraft and what type of fuels they're able to accommodate? London, for example, has 5 airports. Maybe one of them becomes electric only, one of them becomes SAF and hydrogen, and so on.
I'll start if you guys like. Yeah, I mean, we'll be able to fly on both Jet A and SAF. I think the more interesting part of the blended wing body discussion gets when we get into hydrogen. High energy density by pound, but very voluminous. But the unique configuration of the blended wing body allows us to, in a very economical way, store a lot of hydrogen and take our 250 passenger aircraft down to about 190, 200 passengers, and potentially have 3,000 plus nautical mile range, meaning it could fly a series of routes and come back to the hub that has hydrogen at it. So every airport might not be affected by that instance.
I think we talked a little bit about this over lunch. So when you look long term, you look at hydrogen, all these things, that's much longer term than certainly we're looking at right now. So that challenge needs to be, crossed. The big issue, of course, is if you're building an airplane that's fueled by hydrogen, you got to have a system that can support that, which means lots of airports have to have it before you deliver the first airplane. The nice thing about SAF is you're designing an airplane that can take either fuel. And so you don't have to have SAF at every airport to be able to sell an airplane that can use SAF. So there's a huge benefit there. The other thing about a truss brace wing, which it's sort of related, but we haven't talked about was, with the high wing configuration, you've now opened the door to basically allowing the airplane to evolve with larger propulsion systems, more advanced propulsion systems over time. So that also gives you a benefit with that configuration to kind of evolve over time to the fuels or to more advanced propulsion systems.
Okay, I think we have time for one last question.
Yeah, just one quick comment. I'm going to suspect that the differences between the fuel systems and propulsion system on a blended wing body, as you guys imagine it, and the TTBW are pretty similar, right, in terms of the types of fuel that we could accommodate. So if you just isolated the fuel systems, I'm not sure the airplanes would be that different. So probably some commonality there that will remain into the future.
Thanks, Eric, for that add-on. I think we have time for one more question before we close. Bruno?
I didn't introduce myself previously. So Bruno Stoufflet, from a former CTO of Dassault Aviation. You didn't address the question of the definition of ice protection systems. And you know that these last years, the certification agencies have strengthened their requirements regarding these systems. So how do you see the certification of your new configuration, very innovative configuration, knowing that for conventional aircraft, we rely sometimes on return of experiment of previous configuration when we are not too far from the previous ones. So how do you see this challenge issue?
Yeah, it's a really great question. X66, just so you know, will not have any ice protection on it, right? So we get to fly severe clear. We'll just stay out of trouble that way. But again, we're pretty good at knowing how to de-ice engines and wings right now. The only difference on X66 is what do you do with the strut, right? And so, like, given the volume, that's probably some sort of electric heating element to de-ice the strut. But the leading edge of the wing will almost certainly be electric anti-ice, just given the volume. And the engine anti-ice will be very similar to what we do today. So while we need to go do some more research to figure out how we would go de-ice that strut in the most efficient way, we don't actually see that as being a long-term problem with the configuration.
Yeah, and typically we do not de-ice the inboard part of the wing because, but the outboard part of the blended wing body configuration is the same as our current airplane. So, but every time we do internal testing, we also test eye shapes, both for 3-inch eye shapes, and we test also for delayed turn-on eye shapes. And so we know from internal tests how different they are from our current aeroplanes, and we take that into account. I don't think it's a big showstopper for this configuration for us.
I'm just going to add one quick thing. So there was, I mentioned at the beginning, the way we did our proposal process was, basically tell us all the technical questions and uncertainties that you need to resolve. And some of those could be on the program, but there could be some others that are going to be accomplished in another way. And so with regard to icing on a transonic truss brace wing configuration, NASA has another project that is a research project that's been doing work on truss brace wing for a long time. And they're actually going to go into the tunnel, into the icing tunnel at NASA Glenn, and do some testing with the truss brace wing to look at the sensitivities, what type of ice buildup they get, and things like that. So there is research going on for that purpose.
So I think we're going to close the session, and before I do, I just want to thank Rich and Axel and Paul for inviting us to hold this special session on demonstrators, and the rest of the organizing committee, Chris, your whole group for supporting it as well. And then finally, the speakers who have done a wonderful job this afternoon, both presenting and I think taking questions from the field. So one last round of applause for them. And we thank you for your time and attention. Really appreciate it.